Alright guys, in today's video we're going to be looking at this concept of an object traveling under projectile motion. So basically what we're going to be doing is combining our kinematics in our horizontal reference, so our x direction, as well as our free fall motion, objects traveling in the y direction. So when we think about this motion that's taking place in both the x and the y direction, we have to keep the two coordinates separate from each other. So any speed we have that's affecting our movement in the x direction, completely independent from our speeds affecting our movement in the y direction. So we have to keep the two separate. So what's happening at any time an object is under projectile motion is we've launched some object, we've given it some sort of starting initial velocity, and it's going to be traveling only under the influence of our force of gravity. So our acceleration is really only coming from gravity as our object travels through the air, again moving both horizontally and vertically at the same time. So when these objects are undergoing projectile motion, the object will follow what we call a parabolic path, again more or less mapping out the shape associated with a parabola. So there are two types of projectile motion we'll look at. I will begin with this video with looking at an object that has a horizontal initial velocity, right, kind of like this guy driving across a cliff with a bike. He's moving to the right here. Then once he's off the cliff, he's again in basically a state of free fall, but also moving horizontally, follows his curved path going downward. The next video is going to then look at an object that's going to be launched off at an angle. We'll have to think about the fact that our starting velocity has both an x and a y direction to it. So a couple things we'll do with this is that when we are going about analyzing a given problem, figuring out what we know and don't know, I'll still be kind of making our table of values for initial position, final position, initial velocity, final velocity, acceleration, time. Only difference is now we can we'll have to split it up into what information is related to our x direction and looking at then what information related to our y direction. So when we ultimately go to choose one of our kinematic equations to analyze this scenario, we can really only use information in our x column to plug into that equation, or we can only use information in our y column to plug into the equation. We can't be mixing, matching, say, initial velocity in the x direction, but plugging in the y acceleration, right? That can't happen in the same equation. We have to have one just for x and one just for y. So when we think about projectile motion, there's always going to be a given that we can plug into our table. So first step, plug in our acceleration in the x direction. It's always going to be 0. Basically what's happening is once we've launched something, right, there's nothing that's going to be applying a force horizontally anymore, right? Let's say you throw a baseball, if that baseball had a motor and an engine attached to it that kept moving it, accelerating it horizontally, right, that would be a whole nother scenario. But the second you throw that baseball, right, there's nothing that's pushing it horizontally anymore. We have no acceleration in the x direction. Basically means our velocity in the x direction has to be constant. In the y direction, on the other hand, right, we basically have a free fall scenario. Our object's going to be under the influence of this force of gravity. Gravity is going to be accelerating our object downwards at this rate of negative 9.8 meters per second squared. Again, oftentimes if we're dealing with a multiple choice problem, we'll just use negative 10 to simplify our calculations according to the College Board system. But we have, again, this negative value g representing our acceleration is going to be downwards. Again, in these moments, very strongly recommend setting up our coordinate system in such a way that up is going to be our positive direction, down as our negative direction. Now, when we think of this, right, there's this very famous problem in physics that says if you were to take a bullet and you fire it horizontally out of a gun, and at the exact same time a bullet is dropped from the same initial height, we don't know which hits the ground first. So this very famous scenario, right, what we actually find is that both bullets will hit the ground at the exact same time. The reason for this has to do with kind of how we can relate time back and forth between the x direction information and the y direction information. So for the x direction, let's say an object, maybe you shoot that bullet out of a gun and it travels 20 meters horizontally. Right, the time it takes that bullet to travel 20 meters horizontally is going to be the same amount of time it's going to take for that bullet to go from its starting height, drop down to the ground. So what ends up happening is that the velocity in the x direction, all that's going to do is impact how far we travel. It's really our motion in the y direction that's going to determine how long we're in the air for. Right? Basically, you're saying, how long does it take that object to fall back to the ground? So if we go back to that bullet dropped versus bullet fired scenario, right, even though they have different velocities in the x direction, right, the dropped bullet has an initial velocity of 0 in the x direction, whereas the bullet, again, whatever the muzzle velocity of the gun is that's shot out, right, it's going to have some sort of non-zero initial velocity in the x direction. However, both of them are going to have no initial velocity in the y direction. So because of that, our initial velocity is going to be the same in the y direction. Our initial height is the same in the y direction. And lastly, for all objects, right, acceleration is the same in the y direction from free fall. So because of that, all of our kinematic variables are the same. They'll be traveling for the same amount of time. So just to look at a calculation-based example of this, right, we're going to take that same bullet shot horizontally. We're now going to give it a few different measurements. We're going to say we're going to be firing it from a height of 1.5 meters, and it's going to have a horizontal velocity here of 200 meters per second. Again, typically when we're dealing with kinematics problems, where we're told to ignore air resistance, eventually later on in the year, we'll add in air resistance, kind of look at how we can use a little bit of calculus to analyze those scenarios. But right now, we're going to be ignoring air resistance. So when we think about how we can then fill in our table of values for this, again, we want to split this up into both the x and the y direction. We're going to have our initial position, final position, initial velocity, final velocity, acceleration, and time. So because we have projectile motion, we're following this parabolic path down to the ground. Right away, I know that my acceleration, I can fill in for the x direction is going to be 0 meters per second squared. And I can plug in negative 9.8 meters per second squared in for the y direction. If I'm thinking about my starting position in the x direction, right, basically I'm going to say that the bullet's going to start at a position of 0 meters. It's then going to end up at a horizontal position x, right? That's ultimately what we're trying to find in part B here, right? Is how far does the bullet travel? Our initial velocity in the x direction, we're told we're fired 200 meters per second horizontally, and because our acceleration is 0 in the x direction, right, means that our acceleration is going to be constant here. So we'll still be traveling at 200 meters per second horizontally at the end. We don't yet know what the time is going to be. In the y direction, we actually do know the starting height of the bullet. Right? We know it's going to be start off 1.5 meters off the ground. After that 1.5 meters, right, it then drops to ground level. We're going to call ground level a height of 0 meters. Now, one thing that can sometimes be tricky here is because our bullet is fired horizontally, there actually is going to be no initial vertical y velocity. So our velocity is going to be 0 meters per second in the y direction initially. And our final velocity in the y direction, that's the speed at which we are moving downwards as we hit the ground. I really don't know what that is, because we do not know how long we're going to be in the air for just yet. So time, just like on the x direction, is going to be unknown in the y direction as well. So first thing we're going to have to do here is we want to solve for the time it's going to take the bullet to hit the ground. And for this, what we can say is that typically, again, the time that we're in the Air Force is going to depend upon our motion in the y direction. So not always, but I'd say 90% of scenarios we're going to have kinematic information that's going to lead us to want to look at the y direction to solve for time. This one, again, when we compare our tables, also going to make sense. We have a little bit more crucial information of positions unknown for the x side than we do for our y column. So if we're looking here in the y direction, all right, we're solving for time, so we won't know our equation has to have t in it. And we do not have a final velocity information here, so that's going to prevent us from using any equation that has a v in it. So our only possible kinematic equation we can use is we'll have our our final position in the y direction will be equal to our initial position in the y direction plus our initial velocity multiplied by time plus 1/2 times our acceleration in y multiplied by t squared. So here when we're going about this problem, we can only use values in our y column here. So our final height, right, that's going to be 0 meters on the ground. Our initial height is going to be our 1.5 meters that we start off at. Our initial velocity is going to be 0 in the y direction, multiplied by t. We're going to have 1/2 times our acceleration of negative 9.8, multiplied by t squared. So at this point, basically we have an equation where we're trying to solve here for t. So simplifying this, we have 0 is equal to 1.5. Again, 0 multiplied by t goes away, so we're going to have then minus 4.9 t squared. So it's just completing the algebra. Right, 4.9 t squared, when we add it over, is going to be equal to 1.5. After dividing both sides by 4.9, we're left with t squared is going to be equal to 0.3061. Again, solving for actual time, we have to square root both sides. So we find out that our bullet's going to be traveling in the air for 0.55 seconds. All right, so now that we know that our time is going to be 0.55 seconds, right, that's going to apply to both the x direction and the y direction, right? Time is independent of direction. It's a scalar quantity. Be the same for both x and y. So we're now in part B, if we're then trying to figure out the horizontal distance we travel. Right, we're going to be looking here in the x direction. We can use the same kinematic equation, except now again we'll swap it out for x's instead of y's because we're looking at the horizontal motion. So final position would be equal to our initial position plus v initial t plus 1/2 8t squared. So our unknown final position would be x. Our initial position we said was going to be 0 in the x direction. Our initial velocity is 200 meters per second. We're now going to be multiplying by the time we just found up in part A of our 0.55 seconds. Then we have 1/2. Acceleration is always 0 in the x direction. Multiply by our 0.55 seconds, which gets squared. So here, nice thing, again, because our acceleration is 0, this last term is going to cancel out. All we have to do is 200 multiplied by 0.55. That's going to tell us we're going to have our bullet's going to travel a distance of about 110 meters horizontally in those 0.55 seconds.